overview of planning. My name is Dustin Dannenhauer. I'm a student at Lehigh University, working with Mike. He's on my committee and the lab here. And so I found these quotes that I kind of like, because these people said these quotes, nothing to do with artificial intelligence or things, and they're kind of somewhat applicable. So we need plans to achieve our goals, and a lot of my research focuses on how do you deal with unexpected situations where not only may you need to replan because your original plan isn't working, but you may need to change your goal. So it may even go a step more because your original goal is not valid. So I'm going to be talking about this phase in the cognitive level plan phase. And so this is kind of a tutorial, a little bit about planning. So if you already know a lot about planning, might not be too much new. But then I'll also talk about how the implementations are in MIDCA. So right now in MIDCA we have 3 planners. We have PyHop, which is a Python version of SHOP, which is a hierarchical task network planner. I'll define that in the next slides. JShop, which is similar. It is a more robust planner, and it's written in Java, hence the J. And then we also have a heuristic search planner, which was recently added, and that's a state space-based planner. So now, okay, the traditional model of planning is that you are given a goal, a starting state of the world, and a domain model. So the domain model has the actions that you can take, and it defines when you take an action in a state, what is the subsequent state you reach. So if I have a cup and I execute the action pick up cup, the state has changed. Now the state has cup is no longer on the table and it is in my hand because I executed that action. So that information is encoded in the domain model. That's what planning algorithms use to advance the starting state to the goal state. And so given those 3 things, the end result is a plan where you have a sequence of 0 or more actions transforming the starting state into a state that contains a goal. The reason I say 0 is the special case when the goal is already achieved in the starting state. So the one thing I want to say is that AI planning is a major research area with a rich history. The International Conference on Automated Planning and Scheduling has had at least 29 conferences since 1990. And they have just done an intense amount of work, and there are whole courses taught on planning, so this is just a very brief overview related to MIDCA. So I'm going to use an example of the NBeacons domain, which is a new domain added to MIDCA from my research. And the basic idea is that you have an agent, you have beacons in the environment. The numbers are just identifiers. They're all similar, they're all the same beacon object, and there are sand pits. And so the agent has goals to activate beacons, and it wants to avoid the sand pits. If it gets stuck in a sand pit, it has to execute extra actions to get out of it, and it delays the amount of time it's able to achieve its goal. And so what we have here is we have a starting state, which is, I'm showing you an ASCII representation. The starting state. The goal in this case is to activate beacon 6, and the actions that are part of the domain model are movement in each of the cardinal directions and to activate a beacon. So fairly simple. Now what does a plan look like? A plan looks like this, where an agent, so this is a resulting plan after planning is finished. Agent moves east, moves north, moves east, moves south, activates the beacon. If you notice, the agent avoided a sand pit there, which would have taken longer if it would have gotten stuck in that and had to execute it. So this is planning. Now, I'm going to talk a little bit about state space versus HTN planning. HTN stands for Hierarchical Task Network. The reason I'm talking about this is because if you want to use MIDCA, then it's important to know and think about what kind of planner you would want to use, because it depends on your domain. So in NBeacons, there's a reason I used a state space planner and not the HTN planners. But in many domains, you can choose what's best. So the way state space planning works is that on the left, all the way to the left here, we have a starting state, and then all the possible actions that are applicable to, that can be applied in that state are applied to generate future states. So here, I'm showing 3, really there would be 5 because there's 5 actions, or 4, only 4 would be applicable because there's not a beacon in that location where the agent is, but the agent can move in these directions. And so these generate future states. And so this is all during the algorithm. So now, from this state, we generate more actions. So now that the agent has moved west once here at the top, it can activate that beacon. It can continue moving west. It can move south. It can also move east and north, etc. So this process continues. You keep applying actions to the intermediate states to produce future states until a goal is reached. And then the plan is the path along the way. So if our goal is to have beacon 0 activated, and we are in this start state all the way to the left, we need to move west, execute the move west action, and then the activate beacon action. So our plan will be a 2-step plan with those 2 actions. Now, with heuristics, you can trim the number of choices that you're searching, which makes it a lot faster. But this can be, in general, it can be slow, like I was mentioning during the brainstorm. So hierarchical task network planners are fundamentally different. Along with what you're given below, the domain model now includes tasks and methods. And essentially, goals are translated into tasks, and then methods contain domain knowledge. And what this means is that instead of searching, from a state and then seeing what actions apply and then getting subsequent states, instead you're saying, is this method applicable? And then the method, you decompose that into subtasks, and then you search over that. So the search is happening over these knowledge artifacts that are contained in methods, instead of just seeing what operators are applied to the state. So you have, in hierarchical task network planning, you have complex tasks being decomposed into simpler tasks until you get operators, which are primitive tasks that can be immediately executed. And knowledge is encoded in the methods, which tells you how to decompose. And so the search happens over the methods and tasks instead of what actions are applicable to a state. So this is a little dense. Actually, I don't even know if you can see this with the resolution on the stream, but I can still talk about it from a high-level perspective and give you an idea. So this is a method for moving blocks in blocks world, and this first part is what is needed from moving block X, from block Y to block Z. So X is on Y, and it's going to be moved to be on Z. So in that situation, if the preconditions are met, then the subtasks are produced as, so it's like these subtasks are produced instead of kind of making an analogy to the state space. The state space would produce a future state, and then you could apply the actions. Methods produce subtasks, and those subtasks lead to future methods until all of your subtasks are primitive. So here we get the 2 actions, and this order is important. So we get the unstack. So we're going to unstack X, then we're going to stack X, and then we're going to recur to see if there's anything else that needs to be moved, and that's how the methods are decomposed. The main thing I just want to say here is that there are costs and benefits of each. So HTN planners require extra domain knowledge in the form of methods. So you have to say, if in this situation I want to decompose into these subtasks, and it's incredibly faster. I mean, it's in a lot of situations. I don't want to say generally, but it tends to be faster. And state-based, so the nice thing about state-based is state-based planners like the heuristic search, you only need the operators. So you don't have to have these methods. And without any heuristics, it's going to be slow. Because not only are you, in a lot of domains, not only are you searching, this is true in MIDCA, not only are you searching the operators, you're also searching what arguments the operators are binding. So if you have a stack operator, not only are you going to say, I'm going to apply a stack from this state to this state, you also have to say, which 2 blocks am I stacking? And so if you have a lot of blocks, it's a lot of possible stack bindings. So, but heuristics can greatly improve the speed. I mean, heuristics can make it extremely fast, or even domain-independent heuristics. And so the thing is, we added the heuristics search space, the heuristic search planner to MIDCA because we are doing an experiment where we change the operators at runtime. So the domain changes over time, and the effects of one of the operators changes, and we want to update that at runtime. And if we were using an HTN planner, then we would need to, make sure all the methods that involve that task that decompose it have to be modified, whereas in a state space, you just have to change the operators. So that's, if you want to know more, we have like a paper, and you can see the examples and stuff. So now I just want to show, this is an example in the NBeacons with using the heuristic search planner, and in this case, it took 4.5 seconds. But PyHop and JShop are all basically instant for the most part, because the number of, especially in the domains that we have in MIDCA right now, the search space is just significantly smaller. But I do want to say this can be misleading, so don't take this format. So this was run just using Python, but actually if you use PyPy and if you do other things, you can make the search, probably even faster. So, but I just want to show that it is something to think about. Okay, so now I'm going to talk about planner implementation details. So where are the planners even located? So MIDCA modules planning.py is where we have PyHop planner, JShop planner, heuristic search planner. There's also an asynchronous PyHop planner that's used in Baxter Robot. I haven't used that myself, actually, but it is there, and that's what they use for Baxter. So that is where the planning algorithms are. They're in planning.py under modules. Then the planner domain knowledge is separated, and it's under MIDCA/domains. And in this example here, this is a BloxWorld example. So we have domains like BloxWorld and beacons. And that might just, yeah, we have like one other one. And then so you can just look at that directory structure, but the methods that are used for PyHop Planner in BloxWorld are located at this path. Okay, so now an important thing to know about MIDCA is that MIDCA has its own state representations. So it has a world object. It also contains, code, data structures, Python classes for objects, predicates, atoms, operators. It has the world. These are all located in world sim. And PyHop, so PyHop was the first planner in MIDCA, and it was it's been used a lot. And because PyHop uses its own world states and operators, there's a translation function that is needed between MIDCA states and PyHop states. And so just a little anecdote. So when I started working with MIDCA, and I'm just rolling around trying to figure out where everything is. This ended up, like, if I had this presentation, it would have saved me a big headache, because I, had to go find and explore this all on my own. So that's a main reason why I'm putting it here, is that, yeah, Mike has a question.
Is that documented now, so somebody wouldn't have to thrash about like you did?
So, yes. Yes, it is documented. I'm not sure how well. Maybe it could be improved, but it is definitely documented. So what does this translation look like? So it is in, and this has moved, right? So from Matt, when Matt was using MIDCA back in the day, this has been moved. So all the translation, because the translation is domain specific, it's moved under the domains folder. And so these translation functions can be found in util.py, which would be under domains, blocks world, util.py. And when adding a new domain, or if you're modifying a domain, for example, when we were adding mortar to the blocks world domain, we had to modify these functions. So there's a pi-hop state from world and a pi-hop tasks from goals. Both of those are used to get what is needed to initialize the planner. And for pi-hop, which I don't think this is the case with JShop, Zora will talk about that after me, but with pi-hop, once you get a pi-hop plan, you actually have to translate it back into MIDCA actions. So it's really kind of a situation where you are using this planner and you have to translate for the planner to be able to use the knowledge, and then you translate back to MIDCA. But it's all, for what we've done, it's all been quick. But it's important to know, if you want to use pi-hop, this is what it is. So the nice thing is with the heuristic search planner, you don't have to do this. It just will work with the operators and states of MIDCA. So there's no translation needed. So I'm nearing the end of my talk. I'm not sure how I'm doing on time. The planners that are available for MIDCA are, we have a pi-hop planner that is a heuristic task network, JShop planner, heuristic task network. We have a heuristic search planner, which is state-based, and we have an asynchronous pi-hop planner, which is used in Baxter. And in general, HTNs are faster, but they need extra knowledge, and they may need translation back and forth. Heuristic search planner works directly on MIDCA states and operators. The nice thing is you can use it default right out of the box, but if your domain has a lot of objects and atoms, it's really slow. So you have to think about giving it heuristics, and great. It looks like I'm out of time. That is an overview of planning in MIDCA. Does anyone have any questions?
Because we'll still be talking about the planner, why don't we continue?
Yeah, let's move on.
Presentation.